Assalamu alaikum dear students. Welcome to lectures of classical mechanics. In this we will discuss the solution for the problem number 7.15, which says that a pendulum consists of mass m and suspended by a massless spring with an extended length b and spring constant k. Find Lagrange equation of motion. So if I go to the diagram of this question, so it is like this is the spring block system, which is making some inclination theta, and this has spring constant k, and this is mass m, and the length of spring is b, which is unextended length of spring b, and l is the variable length of spring. When spring is extended or it's elongated, so its length will be represented by L and its original length is B. So we can find the kinetic energy and potential energy for this spring system. So kinetic energy will be nothing but equal to m over 2 x dot ka square plus y dot ka square, and you know that this has to coordinate. If we consider this our spring block system, we can find x dot and y dot using this polar coordinate. X is equal to r cos theta and y is equal to r sine of theta. We can take x dot and y dot and substitute in this equation, so it will give m over 2 r dot square plus r square and theta dot square, which we have already evaluated in the previous question. We will not go into this detail. And potential energy will be equal to mgy plus elastic potential energy of the spring, which is just equal to k over 2 and x square. So x square is equal to elongation, which is equal to r minus b. So r is the original, r is the extensions and b is the original, so the difference will be r minus b. That will be the just change in the length, r minus b whole square. So when we put this u, potential energy and kinetic energy, in our Lagrange equations, so we can also write potential energy expression is equal to u is equal to k over 2 r minus b whole square, and we know that y is equal to mgy. So y is equal to r cos, we can resolve this y into two components. X will be equal to r cos theta by sin theta, so we can write this y is equal to mgr cos theta, and so it will be equal to t minus u m over 2 l dot square plus l square theta dot square minus 1 over 2 l minus b square plus mgl cos of theta. So when we put this l into Lagrange equation, it will give the Lagrange equation for this l and theta will be equal to d over dt partial L over partial theta dot minus partial L over partial theta is equal to 0. This will give us equation of motion in theta coordinate, and when we put this Lagrangian, our Lagrangian into Lagrange equation, so it will give expression like this: m r double dot minus m b theta dot square minus this is equal to this. And thus we can simplify this for this r double dot. When we multiply this, divide this m on the other side, will go. Similarly, this is equation for the generalized coordinate r, and this is equation for generalized coordinate theta. This is our equation of motion for theta coordinate, and this is equation of motion for r. So we will need to put this Lagrangian into two equations. First, partial r dot minus partial L over partial r. When we put this Lagrangian into these equations, so it will give this equation of motion, and when put this equation into theta, partial theta dot minus partial L over partial theta, which is equal to 0. When we put this Lagrangian into this equation, and we will take partial theta dot partial L over partial theta, then its time derivative, so it will give 2 mr theta dot plus this whole term. And if we want to arrange this equation, so this will give us this equation.